Ready for more of this nonsense? So what I want to do in this second half then is to actually carry out some calculations of one-point functions. And this will be done by means of, well, the basic theorem I'll do is due to Dew. It's a very famous paper by Dew, which contains a wealth of new ideas, published in 1990, I think it was 91. And in particular, it discusses the question of modular invariance and one-point functions, end-point functions, things like that at genus 1, and amongst other things. But so what I'm going to do is prove a version of Dew's theorem for these one-point functions, and it'll be based on the technology we talked about in the first half. Particularly, I'm making use of the locality formula, which used to be up around here somewhere, and then what will naturally arise from the definition of these 1- and 2-point functions are these elliptic functions that I spend so much time defining. Okay, so let's talk about this then. So I'll talk about basically Dew theory. And I will introduce the notion of what's called a 2-point function in a moment. So if I say 1 and 2-point functions. Now, I spent some time in the first half talking about writing the Weierstrass function and elliptic functions in terms of these sort of Fourier variables. And so the mapping z goes to exponential z. If I talk about z being periodic in 2 pi I, then qz is a mapping from the cylinder to the plane. So it's natural then to actually try to develop a theory of VOAs, making use of these variables, qz, rather than the original variable z on the complex plane. So this is one of the things that Dew developed. And so what I'm going to do is write down some definitions. I'm not going to actually prove very much at this level for an alternative way of describing vertex operators with the same vector space, but it's a different set of vertex operators. And actually, it's an isomorphic VOA in the sense it has the same algebraic commutation relations and so forth, but it has a different definition of the Virasoro, and it's expressed in terms of the variables qz rather than the variable z. So it's a way of kind of carrying out this exponential map in the context of VOAs. So Dew introduced this is one of the reasons why I use the bracket notation as well. What do you call the square bracket? Or sometimes referred to as the cylindrical VOA. V. So this is the same vector space. We have square bracket vertex operators, a new definition of the Virasoro. Let me put this in the wrong order. There's the same vacuum and a new definition of the Virasoro vector. And how is this thing defined? If I take a vector u in the vector space, I use a square bracket notation to distinguish this from the original vertex operators. It's defined in the following way. It's defined in terms of y, y of qz to the L0 acting on u of qz minus 1. Okay. Where qz to the L0 of u, well, if u is of weight u, this is just a multiple of qz. With weight u. The appearance of the minus 1 may appear slightly surprising, but in order to make sense of a formal expansion, basically the reason why the minus 1 appears there is because qz minus 1 then is equal to z plus order z squared. Okay, so it makes sense then to have an expansion in terms of, which is originally here given as some formal variable. Say this is equal to w, for example. You have an expansion in w's, then you can make an expansion in z and compare term by term and so forth. So that's where the minus 1 comes from. Okay, so and what you showed is that this is isomorphic. To the original VOA. And sorry, I didn't give a definition of omega tilde. Omega tilde is the original Virasoro vector, and then we subtract off then C over 24 times the vacuum vector. Okay, so you just have to work through the technicalities to see that this indeed does define an isomorphic VOA. And so for every vector in our original vector space, then you can write down this other set of operators, and they have modes which are notated in the following way. There's some notation here. So this is the sum over n, and square bracket modes. Here's the minus n minus 1. And for example, then we have for this omega tilde, then we have L square bracket of n minus 2. Where the square bracket L's form a Virasoro algebra, which is isomorphic to the original Virasoro algebra. Same central charge, of course. So in particular, there's some special examples that one can work out that I'll do in a moment. But in particular, the V has a grading with respect to the square bracket L0. So I'm going to denote this by Vn, the square bracket n. It's the states in V such that L0 of U is equal to L0. Okay, and this grading is different to the original grading. Okay. But from the point of view of the algebra and everything else, it's exactly the same VOA. I just have imposed a different grading on the same vector space, different set of vertex operators, okay, which are related to the original ones in this way. And if we look at the commutation relations, like the general ones that Jeff was talking about yesterday, it's exactly the same set of commutation relations, but it's just a different set of operators. Okay, in fact, this is a game that can be played in more generality. There are different ways of defining Virasoros and so forth, so one shouldn't come to the conclusion that for a VOA there's a unique Virasoro. That's far from being the case. You can make different choices of Virasoros and grade your vertex operator in different ways and still play around with these theories. Okay, so, and it's this set of operators that naturally arises and naturally will be used to describe one-point functions. Okay. In particular, we're going to see there's a direct correlation between the square bracket weight of a given vector here and its modular, its weight as a modular form. Okay, it's that weight which is used to determine the weight as a modular form. Okay, now you can find a formula that tells you how to translate between the square bracket modes and the round bracket modes. And the details of this appear in the appendix. And in particular, we have for m greater than or equal to 0, this is equation 33. We have the following formula of the square bracket for any vector v, for v of round bracket weight and 0 weight v. We have this horrible formula here, which I'm not sure why I'm writing it down, but anyway, here we go. Okay, actually, there's a particular formula, some coefficients times vi. I is greater than or equal to m. Okay, so the square bracket modes in general, in fact, correspond to an infinite sum of round bracket modes. And you can invert this relationship as well if you wish to. Okay, and so you can see this in equation 33 and 34, the details of that, and the appendix. In the appendix, I've actually done some calculations to show you how to prove some of the relations shown there. And in particular, there's a nice relationship between the sum over these modes and the sum of these modes, which goes as follows. In particular, and this is a formula that's going to appear in our deliberations, the sum over I greater than or equal to 0 of k, choose I, vi, is the same as the sum over m of k plus 1 minus the weight of v to the power of m over m factorial vm. Okay. So if you're interested, you can read the appendix, and this can be proved just by this the combinatorial identity. Right, an appropriate expand. It's a simple application, in fact, of the binomial theorem ultimately to prove this. it's no big deal. That's a good question. What's K doing there? Yes, any K, thank you. Yeah, thank you. Yeah, that's right. Thanks. So you may recall, or you may not, that something like this appeared in the commutator formula. There was a binomial factor with something like this. So this is going to be used when I apply the commutator formula. I'm going to translate from a commutator formula in terms of the round brackets, and then shift over to the square bracket notation. And then you'll see that expressions of this kind, actually, when I resum, are going to result in these elliptic functions that I defined. Okay? So, okay, at one level, this is very technical. There's lots of notation stuff, but actually, it's just a matter of just turning the handle and calculating. It's not deep mathematics, nothing like that. It's just the result may be deep, but the actual technique is very much just following your nose and just calculating, and then you get the answer. Okay? So, and this identity will play a role in all that. Okay, so now let me come to some definitions. I mentioned the term one-point function, two-point function, and let me define these things, and partition functions. Okay, so this is all in the torus. So the torus, I guess, is 0 point and to 2-point functions. So again, this ties in with what Jeff was talking about. So we define the partition function, or the 0-point function for a VOA. I'm going to denote it by ZV, so V refers to the VOA, of course. It's a function of, well, it's a function of tau. It's the tracing over this vector space of Q to the L0 minus C over 24. Okay, so this famous C factor is going to appear there in the exponent. Or you can write this, of course, as the sum over n equals 0. It's the dimension of Vn. So, as Floyd asked, this is finite, so that's important. So this is Q to the n minus 2. So it's a graded trace. And so each individual grading is finite dimensional, and so it's just a straightforward definition. Well, in general, you might ask the question, for example, when does this thing converge? Okay, under what conditions should this thing converge? It has a pole for C is positive. It has a pole at Q equals 0. Does it have poles anywhere else? Okay, and these are the sort of issues that Ju's paper is all about. Okay, so for certain kinds of VOAs, you can, of course, work with certain examples, and I'm going to do some examples in a moment, and you can see that this is going to give you some nice kind of function. You can just check that it converges, and indeed it has nice modular properties for appropriate VOAs. But in general, Ju's theorem tells you when this thing converges and when it's modular. So that's pretty deep. Okay, and then furthermore, we can define the notion of a one-point function, which I already defined before the break. CV of a vector V, let's call it U, so I'll get my U's and V's mixed up, is a trace over the vector space. And I just stick in this level preserving operator, OU. Okay, now I want to point out the following simple observation. You can also write this thing here. Okay, so here I've taken one particular part, if you want, of the vertex operator for U, that being the level preserving part. But what I want to talk about now is the notion of the two-point function, or another way of thinking about, and also another way of defining the one-point function, where we not just put in a particular mode, but actually insert the entire vertex operator in here, okay, and see what happens when you trace it. So if I put the entire vertex operator for U in here, only the part which is level preserving is going to contribute, okay? And it's a question then of just tracking through the powers of Z and so forth to see that I can indeed get precisely this definition if I write down the following thing. This is the same as the trace of Y. I'm going to write something down which is very similar to my square bracket definition here, but it's not quite the same thing just yet. Okay, so there are some technicalities here which are unfortunate, but that's life. I'm defining the following thing. Okay, so the aim here is to think of some way of actually inserting the vertex operator, not just some mode of the vertex operator. And when you insert a single vertex operator, well, only one contribution is going to come out of this. So it's easy to, if I track through this is the same as the sum over n. I'm going to have un qz to the minus n minus 1, but also I'm going to pick up a term from here of qz to the weight of u. Okay, so I'll assume u here is of weight u. And then you see that indeed only the 0 mole contributes. Only when n is equal to the weight of u minus 1 will this term here contribute. So this is the same as if you want O of u plus qz minus 1 qz terms, okay? Well, or the qz. Okay, I'm being very rough and ready in that. So it's O of u plus terms which go like qz to the minus 1, whatever, and terms that go like qz, negative powers of qz and positive powers of qz. And so only the level preserving term contributes. And so the net effect of this term, this extra contribution here, is just to get rid of any power qz. That's all I'm talking about here. Okay. So even though I introduced z in here as a parameter, in fact the thing is independent of z. Okay, so it seems a bit silly. So I've made something much more complicated than it originally was. But the point is, this is the natural way in which to consider the notion of what are called two-point functions, or indeed n-point functions, where you can insert many of these vertex operators in and try and compute a trace. And it's natural, as I'll try to demonstrate in a moment, that one should look at expressions of this kind. So what happens, for example, if I put two of these operators in? And this is what's called a two-point function. So I'm going to have to cut short some of the discussion if I get to the main point here. So let's define that two-point function. Oops. So this is defined in terms of two. I'll use f to denote two-point function distinguish. We have enough z's lying around at the moment, so I'll use f here. So I say it's defined as a function of two vectors, u and v, say with parameters z and w. It's a function of tau. And it's defined in the following way. I take the trace over v, and so I'm going to insert two of these guys here. So I'll say qz, 0. Sorry, qz, y, qw, v, qw, q to the L 0 minus 0.24. Okay, and indeed you can keep putting more and more of these in if you want to. Okay, so this is my definition of a two-point function. So it's I'm trying to get motivated in this sort of silly way by saying, well, this trace here is the same as this thing here. Now, one reason why I'm writing it this way is that what I'm going to show basically is this thing is an elliptic function. This is an elliptic function. Okay, so and it's elliptic in the two variables z and w, so that means it's periodic in z and w on the torus. So it's immediately periodic up to 2 pi I. So if I shift z by 2 pi I, for example, or w by 2 pi I, then it's because it's a function of qz and qw, it's automatically periodic in 2 pi I. What's less obvious is that it's periodic also in 2 pi I tau. And there's a calculation shown there on page whatever it is that shows that fact. And that's not at all hard to prove that it's periodic in 2 pi I tau. So I think I might just skip that part. So what I'm trying to say is this is a natural thing to try and write down. So in, where does it appear? So it's below 39. So it's periodic in 2 pi I tau also. Okay? So that's where these terms here really play an important role. So this looks like a good candidate for something which is interesting. Okay? Now, I have no idea if this thing converges or it's analytic. I'm just saying as in this formal sense it's periodic in both 2 pi I and 2 pi I tau. Okay. And this is the power of Jou's theory, that he can actually tell you not only that the thing really is elliptic, but in fact exactly what it is. Now, furthermore, one last thing I'm just going to quote. Using associativity, And again, this is sketched in equation 39. Using associativity, we can actually combine together. Associativity is a way of combining a product of two vertex operators into a kind of a nesting of vertex operators. So you have, roughly speaking, if you just allow me to, we have the following. Okay, and there are some technicalities here, so I'm going to squiggle here. So this is y of u of z minus w acting on v of w. Okay, so there's a sense in which that can be maybe made precise, but that's the idea. You can actually nest you have this vertex operator acting on v and then take the vertex operator of that. And that's an alternative way of writing the associator that Jeff wrote down yesterday. Okay, you remember he had something which involved a product of u's and modes of u and v, and then something which had kind of a nesting of u acting on v. Okay, so using that associativity, this expression here can be alternatively written in the following way. We find that f, okay, let's write f, is the same as, when I'm going to find y on y acting on, of u acting on v, I find this is the same as a one-point function, following one-point function. It's the one-point function found by taking the vertex operator in the square bracket setting of u of z. Now, I just remembered actually I used different notation in the notes for good reason. So if you forgive me, I'm going to change this to z1, z2 so it fits in with the notes. And remember, otherwise I'm going to get lost in notation. So z1, z2. And indeed, I think I said qi is equal to q to the zi. Okay, so I call that q1. So sorry, just some notational change here. So this is zi goes to zi plus 2 pi I, and so forth. So this is z1. Z12 acting on V of tau. Okay, whereas Z12 is Z1 minus Z2. So when it comes to using the associativity property and some other manipulations which are described here, you end up with the square bracket operator naturally arising. Okay? So this means the square bracket operator for u as a function of z12 acts on v. So actually the 2-point function, the 1-point function which in this definition here had a parameter z is independent of z, and the 2-point function actually has two parameters z1, z2. It's in fact a function of z1 minus z2. It's a function of the difference. z1 minus z2 only. So in fact, this is a general phenomenon of any endpoint function on the torus. The torus has a translational symmetry, okay, which means that any endpoint function is a function only of the differences of the parameters, not a function of the actual parameters themselves. Anyway, so here, that's an example of that here. So I'm going to make use of this in a little while. So I have this notion of a 2-point function, which is defined by this horrible thing here, okay, and has various properties. If we're analytic, for example, then I can conclude it's actually an elliptic function. But it's easy to see it's certainly periodic, so it looks like a good candidate. And furthermore, we can see it's going to be an elliptic function actually of z12, of z1 minus z2. Okay? So what I'm going to find is that this thing really is an elliptic function, and I might as well give you the answer. And then I'll try and spend the next 20 minutes proving it and then do some examples. So what's the answer? So f, I'll write that again, of u of z1, z2 is the following thing. We've got a term which is the trace over v of OU times OV times q to the L0, 4. Okay, so those are the level preserving parts. Okay, they're independent of both of z12. And then we get this, it's a bit like a Taylor expansion, but it's kind of a truncated kind of Taylor expansion. Sum over m greater than or equal to 1, minus 1 to the m over m factorial into p1, the nth derivative, is the function z12 of tau. And then what's sitting here then is zv of u square bracket of m acting on v. And this truncates, so it's a finite sum. For the same reason talked about before, that u, m, and v will eventually vanish where m is sufficiently large. And these objects, these functions here, are the P1 functions that I spent half an hour talking about this morning. Okay. So it's an explicit formula that tells you that, I suppose the sequence in which this is developed by Zhu is to prove this formula, is to prove a formula where z1, z2 are really formal variables, and then to be able to identify these expressions here, and then invoke the fact that these in fact are analytic functions, okay? And so in fact you can really think, you can go back there and really think of z1, z2 here as being complex parameters on the torus. And so the thing is truly an elliptic function, and further than that, it's explicitly indeterminate. Okay. This formula also allows us to find a recursive kind of identity for one-point functions, which I'll come to in a moment. When you use that together with this relationship here and expand it in terms of z1, 2, we'll have a recursive identity for one-point functions, which I'll talk about. So let me give some idea how you prove this. I'm not going to prove it in all detail here in the board, but it is actually there in the notes, and it's about a page. Okay, well, it is actually, yes. So, it's not so bad. The key idea, well, there's two key ideas. The first is to make use of the commutator formula, which follows from locality. You make use of the commutator formula, and then I use, I probably just wiped off the board, did I? It's gone. Use the commutator formula together with the formula that relates to sum over round bracket modes, so square bracket modes. Remember, I pointed that out. And then lastly, we make use of identity. We all learn in second year in college that trace AB is trace BA. And that's actually what makes the whole thing work. If only we could do this at genus 2, then we'd be so much happier, but you can. So trace AB is trace BA. So all these things are traces. And ultimately, because we have this graded space, I mean, we're invoking this formula for finite dimensional traces over each of the finite dimensional vector spaces. So what I'm going to do is to take my definition of F and start using the commutator formula and take the modes of the first operator and bring it through the trace, okay? Bring it through the trace and then bring it to the front again using trace AB as trace BA, and you get some kind of a relationship between the trace and itself, and ultimately it results in this. Okay, so let me give you a proof of Zhu's theorem. Yeah. What do we have? We know that f of v, I won't write down its arguments again. I'm going to write out the f of v in terms of the modes of the first operator. So I have a sum as follows. Again, this is just equation 941, I think it is. It's q1 to the minus, that's k, is it, sorry. Minus k minus 1 plus the weight of u. So this is the usual term arising from the vertex operator, and this is the q1 to the L0 term, giving that. It's the trace then, over v of u of k. And then I have the second operator, q2 L0, v q2, and then I have q to the L0 minus c over 24. Okay, so that's just writing out the mode expansion for the first vertex operator. So then, as I say, I'm going to take this thing here and just bring it through, commute it through the two terms in the trace. We know how to commute UK with this operator. We also know how to commute this with this using the property I wrote down before of how L0 commutes with UK. And so we end up then with the trace of this operator, the trace of these operators being the same as the trace with UK now appearing on the right-hand side. And as I say, trace AB is trace BA, and you end up with some nice formula. Okay, so let's compute this thing here then. This is the same as the trace of the commutator. And the commutator, this is where it gets slightly messy, is well, even more messy. Is the sum of I greater than or equal to 0. I remember I quoted the commutator at the beginning there. K, choose I. So it's y of u, the ith mode of I acting on this vector here, q2 to the L0, LV, and this is then q2. And there's some other stuff at the end. Then we also have q2 to the k minus I. I'm sorry. Let me just isolate the commutator. Excuse me. So UK of y of Q2 to the L0 v Q2. Okay. So that's the commutator formula I had before, with just with this extra stuff, this the Q2 factor of L0 thrown in. So then it's an easy matter to commute this through here and to work this thing through, and you end up with the following. This is the same as Q2 to the k plus 1 minus the weight of u again, right? And then I'm going to take this sum here. This is linear in this argument. I'm going to write it as y of the sum of I greater than or equal to 0. K, choose I. And then here we have ui, excuse me, acting on v of Q2. Okay, so that's just bringing the Q2 operator through and using the property I mentioned before of how L0 commutes to UI. And then this gets modified in the following way. And then I've taken the sum over the UIs inside the argument. Now look at this thing here. This is exactly the sum over the round bracket modes that I mentioned before. So the sum over the round bracket modes can be written as the sum over the square bracket modes. Okay? So now we're halfway there, actually. So again, this is written out in the notes. Maybe I shouldn't be doing it in such detail, but anyway, I guess there's no harm. So it's Q2 to the, I've written here as Q2 to the n as a sum over m, and this is again quoting the earlier formula. I have n to the m over m factorial y Q2 L0 of u square bracket m acting on v Q2. Where for convenience I've introduced n is just a shifting of this index here. It's k minus the weight of u plus 1 or minus 1. Plus 1. Okay, so it's just so n is just a shifting of k. All right, so now we've done the translation in the commutator from the round bracket to the square bracket. So this thing here, of course, is going to be, where's the result? I'm not organized, but oh, here it is. That's this bit here. Okay, that's the square bracket bit here. So the sum over m is going to, and the m factorial is exactly the sum over m. And we're halfway there. So the rest of it basically is what happens when I go back and put this commutator back in here and sum over k. And that sum is going to involve things like sum over the k is the same as the sum over n, involve things like n to the m and various terms involving q to the n and q1 and q2 to the n, which will be, in fact, this elliptic function. Will be the elliptic function expressed in terms of Fourier coefficients that I talked about. Okay, so then the trace, this trace here of v of uk is equal to this gadget here, factorial of the trace. Well, you see, I now have a trace of a single vertex operator, okay? And this is O of that. So this is going to be Z V of UM. So that's exactly this thing on the right-hand side there. Plus the trace over V, and now I've taken the UK to the side, so I have this Qt2 to the L0, Q2, and now I have UK sitting here, and Q to the L0, minus CO24. Okay. But now it's very easy then to commute this with Q, and you pick up some power of Q when you do that, from the commutator of L0 with UK. And ultimately you end up then with a relationship which says the trace of this is equal to some gadgets, some stuff, plus the same trace, up to some multiplicative term. So let's leave this up here and not delete it. So as I said at the beginning of this proof, you really just keep calculating. They're not invoking any big theorem or anything, or it's just linear algebra and keeping track of things. Okay, so lots of notation, but other than that, it's not very hard. So, so we can commute UQ through this. So UK commutator Q to the L0. Well, sorry. Q to the L0 is the same as Q to the K minus the weight of U, I think it is. Is that right? I always get this mixed up. The wrong page. Where am I? Q to the, it's Q to the, okay, oh, it's Q to the N. I'm using this N here. Okay, so you can work that out. UK, okay, it's an exercise. Times Q to the L0. Sorry, where am I? Okay, so then finally, as I say, trace AB is trace BA, so you end up then with the following formula, and you find 1 minus Q to the N into this trace we started off computing, trace of V of UK, okay. And, using trace AB, trace BA, okay. We've got this very nice formula then, it's Q2 to the N, the sum over M over N factorial. So it's really just locality. At the end of the day, you're just looking locality and commuting things through and just, you get what you get. And this is denoted, I think, by Jeff by M0. Okay. Well, first of all, this is the vector space is spanned by Fock vectors, or the Fermat module is how Jeff described that. So spanned by Fock vectors, and I'm going to use the square bracket determination of that. So we have A minus K1 minus Kn, say, and I can order these. So I'm going to take K1 less than equal to 1, K2 less than Kn. It's so-called Fock vectors. So every vector in my vector space can be taken to be a Fock vector, and so I can just recursively use this identity to actually compute all the one-point functions. In fact, you can compute all n-point functions by this method, ultimately. So, and furthermore, OA, in this case, is A of 0, okay? And A0 on V is equal to 0 for all V in this vector space, okay? So it's the 0, the 0 here refers to the eigenvalue of A0, okay? I think Jeff called it H in general. So A0 is equal to 0. So it's very easy then to compute any Fock vector by recursively using this identity. So let me just give some idea of how that works. I'll just write it down. So I have A, if I take A minus K1, and I'll have A minus K2, blah, blah, blah. On the right-hand side then, this is for the Heisenberg, M0. On the right-hand side, well, this first term only contributes if K1 is equal to 1, okay? But in fact, even if that term is, if K1 is equal to 1, we have O of A, which is A0, which is 0 on this theory. So the first trace here never contributes to 0. And I'll come back to that in a moment as to what happens when you place this by a module. And then the second term, then we can compute this because we know exactly how the Heisenberg algebra works, that A of M, how this should act on a Fock vector. Okay. Plus, I won't write all those terms again, but we have Z of V, of M0, and this time we have AM for M bigger than or equal to 1, acting on the remaining operators in the Fock vector. Okay, but these things have a nice commutation relation. So this is the same. I like this time I will write out the answer. The sum over sum over n, is it? Okay, so what happens, okay, I'll put this in here, but a m commutated with any a minus ki, and the remaining terms here, is going to be equal to ki delta m ki. Okay, so basically you only get a contribution here when m is equal to one of these values of k. All right? And so I can replace the sum over m here by a sum over the values where m is equal to either k2 or k3 or k4, whatever it is. So this becomes a sum over I from 2 up to was it n I call it? Minus 1 to the ki plus 1. Oh, I made a mistake here somewhere. That should be n plus 1. I'm sorry. I think I put a, is that right? Yeah, that's n plus 1 there when you work this out. And then you get the factor of ki coming from the commutation formula, and then we have this binomial factor, and so on and so forth. So the point I'm trying to make here is explicitly, doing this example, you can actually see precisely how this is k1 plus ki. You get this recursive identity. So it's a minus k2 then, down to a minus ki, and this, the ith term is deleted. Down to a minus kn acting on the vacuum. So basically you kind of pick off two at a time, two of these creation operators at a time. And so recursively you can compute any one-point function. And furthermore, this thing here is a modular form of weight k1 plus ki. So what you conclude from all this is eventually everything goes down, and eventually you just get the trace of the vacuum, which is the partition function. Okay, so ultimately, well, you find by iteration that zu of tau is q of tau divided by 8 of tau, okay, where q of tau is a modular form of weight. Well, I use the square bracket thing here. The weight of this state here is k1 plus kn, and it's easy to see that indeed corresponds to the weights of each of the modular forms that arise when you multiply them together. So it's of weight, square bracket weight of u. Yes, thank you. Yeah. It's a quasi-modular form. Why is it quasi-modular? Because E2 can appear in this whole sum here. Okay, so you could have K1 and K2 equal to 1, for example, and you get a factor of E2. So it includes amongst the list of modular forms that arise E2. So there's an exercise there in the notes that says, well, when do you get a modular form as opposed to a quasi-modular form? And you can have a go at that. It's not hard to show. So also, if you allow me, you can take this result here, and it's easy to see what happens if you replace the VOA the trace. Sorry, come back again. If you replace the definition of the 2-point function or 1-point function, whatever it is, by instead of having the vertex operator from the regional VOA, you replace it by a module. Okay, and then you have a trace over the vector space associated with the module. And then all these results go through because the whole thing is based on locality. And of course, the module structure, the representation is also local. So you can, the theorem goes through in exactly the same way. So basically, you can replace every time you see a V here, you can replace it by a module. And it's the same theorem. Okay, and you get a trace over the module. So in the case of the the case of the Heisenberg VOA, if I replace this by a module, and this is unfair thing to do, but I put places by MH with the notation I think that Jeff had. Then all that happens here is this becomes MH. This becomes MH. It's all exactly the same, but there's an extra contribution arising here. I had a vanishing term here because I said that OA is vanishing, but in this case I get an extra term proportional to H. So where will I make that change? Well, okay, make it here. There's an extra term here which is proportional to H, and then we get H into the H, where you have one less term here. That's A minus K2. So again, you get a recursive density that one can work out. So it's no big deal to go to a module in this case. Okay, so I also want to say something about the Virasoro. When you apply this formula to the Virasoro algebra. So what happens if I take, in this formula here, if I take U to be a Virasoro vector? Now, I was going to say more about lattice VOAs, but I'm running out of time there, so you can read that again in the notes of the Virasoro. So if you choose U equal to omega tilde, okay, and then omega tilde of -1 is L of -2. If you remember the relationship between omega and L, and its modes. And then look at O of omega tilde. It's the level preserving part of omega tilde. Well, if you remember what this was, this is omega minus C over 24 times the vacuum. So the level preserving part of omega is L0. And the level preserving part of that is minus C over 24. Okay. So look at that. That's the same operator that's appearing all the time in these Q exponents. Okay. So O of omega tilde is L0 minus C over 24. So ZV of L minus 2 of V is an interesting thing to look at. What happens if you take L minus 2? And this corresponds to K equals to 1, so these formulas are slightly simpler to look at in that case. So we get the trace of L0 minus C over 24, okay, times O of V, Q of L0 minus C over 24. Okay, this sum starts off at m equals to 1, and I have K equals to 1 here in using this theorem, so I'm going to have an E2 term. Let's write that down. When you do that, it's actually plus E2 into Z of L of 1, sorry, omega tilde of 1, let's write that down, is actually L square bracket is 0. Plus, then we have remaining terms, which is for m bigger than or equal to 2, isn't it? And k is 1, so that's E 1 plus m. I can write this in a neater way, but this is sufficient for our purposes. And this is L of m minus 1 or something. V. So we get a recursive identity here involving the L's and the Eisenstein series. And what I want to point out is look at this combination here. This is a big part of Jou's theory, is that this operator arises so that Q, the exponent of Q is L0 minus 0.24, and that's exactly this operator here. So in fact, this is the Q derivative of a one-point function. And not only that, but the E2 factor is coming in as well to give us the covariant derivative, provided what we're acting on is a modular form. So this is the same as Q d by dq plus an L0 acting on V. Well, let's take V to be of weight, square bracket V, times E2 acting on Z V, plus some other stuff, this modular stuff. Okay. Now this stuff is definitely modular, okay, because this is well, actually, it's only the even terms contribute, of course, so it's for m equals 3 is the first term, so it's E4, E6, E8, whatever, they're the terms that contribute. Okay. So this is what I called the modular derivative before. So what happens is the following, is that for Virasoro operators acting on, well, you have this notion of primary vectors and so on. So that you can decompose your theory into primaries, which are lowest weight vectors, the Fermat module for the Virasoro, and then the remaining vectors then can be thought as being Virasoro descendants of that highest weight vector in the Fermat module picture. And then so the one-point functions for the primaries, as long as the VOA is of a sufficiently correct type, will be modular forms, and then you can invoke this thing here, then theorem, to see that actually you're going to get modular derivatives of modular forms. So again, the notes explains an example where you see this worked out in practice. For appropriate VOAs, this is actually, again, Jeff talks about this in his notes on rational and C2 cofinite, or a technical condition. Z of V is a modular form. Okay, it's a modular form. Now, it's not necessarily a modular, well, I've got to be careful here. Yeah, for a subgroup, exactly, yeah. Well, again, you've got to be careful. It's not the full. I was doing some examples here. So it's a modular, okay, I'll say it's a modular, it's a subset of this set, anyway, is a modular form for a subgroup, okay. I've got to be careful, yeah. Yeah, I know. It's a space of modules I have to really consider here. Conjecture. Yeah, I know, conjecture. Well, I agree. It's the set of these things. Okay. So I had an example for lattice where I was going to show you that this is so. Okay, so lattice VOAs and other examples. Okay, this is definitely the case. Okay, and it's conjecturally true. True for all rational theories, actually. I think really conjecturally. We can say I would say rational C2 cofinite. And as part of that, you see the way in which this operator here arises the modular derivative. So one of the aspects of, oh gosh, I'm over time. One of the aspects of Jou's theory is to show that indeed these functions, the partition function corresponds to just taking the vacuum vector here, or indeed any one-point function actually converges and furthermore has its modular properties. And for these kind of theories here, it's possible to actually write down, there always exists some vector which involves Virasoro operators like this, whose one-point function vanishes. And the result is that you get a differential equation for the one-point function or do the partition function. And the differential equation involves multiple, in general, multiple actions of D together with various multiples of Eisenstein series. So again, Jeff mentioned this briefly yesterday. And that's the road to actually showing how the partition function converges on the upper half plane, because it satisfies a certain differential equation which is only singular q equals 0. And then from this q d by q term. And then furthermore, one can show that the set of solutions is modular. So I wanted to kind of touch base with that idea as an example of this. But even just from the point of view of working out, you can take specific VOAs and well, certain kinds of VOAs anyway, and compute all endpoint functions or all one-point functions in this way, and see that the one-point functions are indeed modular functions. Okay, so and there's more details in the notes. So I think we'll finish there. Okay, right, thanks. Okay, so now, if n, remember, is this shifted thing of k, so I'm using this thing here. If n is equal to 0, okay, then you get 0 on the left-hand side. On the right-hand side, you get 0. Everything is 0 automatically apart from the m equals 0 term. So for n equal to 0, this implies 0 is equal to, we get one contribution from m equals 0 there, which is z of u0. Okay, so that particular one-point function always vanishes. Okay. And then if n is not equal to 0, then we get some contribution. So in other words, we can divide by 1 minus q to the n, and now you're starting to see the kind of ingredients we had before. So you're getting q2 to the n divided by 1 minus q to the n, and this kind of n dependence here as well. Okay. So when you sum over n, it's exactly going to be these p1 functions I talked about at the very beginning. So this is kind of the home straight now. So if you follow me this far, don't give up. I'm tempted to quote Howard Greenspan once said that if you understood what I said so far, you haven't been listening. So I'm not sure what that means anyway. So if you divide, so for n not equal to 0, you can divide by q to the n, and then n and k, so this is just a notational thing here. So the sum over k is just a sum over n, and so we end up with the result. So so hence we find that f is the sum over n. So sorry, we have to take out the n not equal to 0 term, the n equal to 0 term, which corresponds to the trace of OU, OV. That's the first term. I have my expansion. This is the n equal to 0 part. Okay, so our k equals to whatever it is, 1 minus the weight of u. So you get OU, and then that's the level preserving part, so you get OV here again. And then what's left over then is a sum over n, not equal to 0. And we get all this junk put all together. I probably wiped out too much stuff to make sense of it now, but anyway. So we get q2 over q1 to the n over 1 minus q to the n, and then we also have a sum. There's a sum over m as well, equal to 1 over n factorial. And we have all this, and this is n to the m, isn't it? Or is it m to the n? N to the m, it is n to the m. Okay, and there's a q1 factor that came in from the original. It's there in the notes, you can see it there. So it's q2 over q1 to the n. And this multiplies what? Y of um v. Okay, so lo and behold, this is the thing I spent half an hour or whatever talking about. This is p1 of m. Now we have to look, it's actually p1 of z2 minus z1, and so I don't know, it's just conventional to write it as a function of the difference, the other way around. So this is an odd function in m. Oh, sorry, it's odd for m even. So it's odd for m odd and even for m even. So it's z1 2. Okay, so QED. So really, this is not so bad. You know, it looks complicated, but the idea is just to use the locality formula, commute everything through, and see what you get. And basically, this can be generalized. You can have many vectors in here. Or sorry, vertex operators. You can consider other kinds of structures, modules, and various things, and play the same game, and get lots of nice formulas. Okay, that's not too bad. Now, how does this? I kind of introduced something a bit more complicated, which is the two-point function, and the title of the thing is modular forms. So let's see how this relates then to, specifically to calculating modular forms. Well, I had this formula which invoked associativity, which allowed me to write the function, the two-point function, as a one-point function. So recall, this seems a long time ago now anyway, that f is also zv, a one-point function of the square bracket of u of z12 acting on v. Okay, so what is that when you write it out in terms of modes? It's a sum over, let's get the right index here. I called it k, didn't I? Yeah, k. Okay, so this is z1, zv of u k acting on v, tau into z12 to the minus k minus 1. So in other words, if I take this expression here, or this expression, I wiped off the main theorem. Well, here's yes. If I take this theorem here and I expand this out in terms of z12, and I identify the powers of z12, I can read off what the one-point function is for uk acting on v. So comparing powers of Z12, we can actually find the recursive identity for one-point functions. Now the left-hand side here, so the right-hand side, this thing here, P1 of Z has a pole of order 1, P1 of M has a pole of order M. So there are singular terms here of order M for finitely many values of M. And so that corresponds to, of course, negative powers of Z12. And so if I compare it to the negative powers of Z12 here on left and right, you just get a trivial equality. Okay, you get literally the trace, the one-point function of UM of V for M negative is the one-point function of UM of V on the left-hand side for M negative. So it's only when K is when you consider K negative here that you get interesting identities. So for K greater than or equal to 0, this is a trivial relationship when you compare both sides. For K less than 0, it's much more interesting. And we get the following formula, CV. So I'm going to write it as U minus K V. So here, I've made a change of notation of the sign there, if you understand what I mean. So so minus K less than 0 trivial. Okay. Oh, sorry. From minus K greater than or equal to 0 is trivial to minus K less than 0. Okay. This is for K positive. So U minus K of V is going to give us the trace of when K is equal to 1, we get the contribution from OU and OV. And then we get an infinite sum again, or sorry, finite sum, which is indexed by M again, minus 1 to the M. And this time we get this binomial factor that I had. I wrote down an explicit expansion for this thing here in terms of Z12, in terms of various binomials. And it's expressed in terms of Eisenstein series. So here's an explicit formula, a recursive identity. It tells you how a one-point function is related to another one-point function of a lower weight. And that's the key thing that I have to really talk about here. Okay, so the conformal weight of this thing here is going to be larger than the conformal weight of this thing here. So basically, you're getting a one-point function recursively relating a one-point function of a higher square bracket weight to a lower square bracket weight. And it's possible then, in many theories, to recursively use this identity and actually to compute all one-point functions. And indeed, for certain general theories, this identity it allows you to prove convergence and various things. So let me try and give some illustrations of that and give some idea as to how that all works. Okay, so I didn't actually do any examples yet of a VOA, so let's just do an example of a Heisenberg. Oops. So the Heisenberg. I'll just do this at rank 1 generated by A. Okay. Well,